All right, folks, welcome back. We're about to start a new chapter here, chemical reactions and stoichiometry. In fact, it seems like one of the things most people think about when they're introduced to their first chemistry class might be the periodic table. But then the next thing they think about are chemical reactions and balancing chemical equations. And that's exactly what we're going to learn how to do today. So chemists use statements called equations to represent chemical reactions. Equations show a reaction's reactants, which are the starting substances, and products, which are the substances formed during the reaction. Chemical equations do not express numerical equalities as mathematical equations do, because during chemical reactions the reactants are used up as the products are formed. Instead, the equations used by chemists show the direction in which the reaction proceeds. Therefore, an arrow rather than an equal sign is used to separate the reactants from products. You read the arrow as reactant to produce or yield. So whenever you see an arrow in a chemical reaction, you're going to think of the words reacts to produce or yields. The reactants are written to the left of the arrow, and the products are written to the right of the arrow. When there are two or more reactants, or when there are two or more products, a plus sign separates each reactant and product. In equations, symbols are used to show the physical states of the reactants and products. Reactants and products can exist as solids, which we abbreviate with the letter S in parentheses, liquids, which we abbreviate with the letter L in parentheses, and gases. And of course we have another when they are dissolved in water, and that is aqueous, which we abbreviate with the letters AQ in parentheses. It's important to show the physical states of a reaction's reactants and products in an equation, because the physical state that might provide clues about how the reaction occurs. Some basic symbols used in the equations are below. So we've already talked about solid, liquid, gas, and dissolved in water. We talked about the arrow and the plus sign. And then these arrows that go both ways we're going to talk about later in the year when we discuss something called chemical equilibrium. So let's try to write a word equation by using these symbols over here, as well as the symbols for the elements. So if I have aluminum, wouldn't that be elemental Al? And obviously that is solid aluminum, isn't it? And I'm reacting with bromine. Now bromine elementally is Br2. We call that a diatomic element. There are 7 of them that we're going to bump into here in just a little while. But bromine should be written in its elemental state as Br2, not Br. And bromine is a liquid at room temperature. And we end up reacting to form, or yielding, aluminum bromide with an S at the end, so that means it's a solid. Now what is that formula for aluminum bromide? Well, hey, we've learned how to write formulas. We have aluminum atoms, or ions, and bromine ions. Let's look up their charges. We have a metal and a nonmetal, so this is an ionic compound. So we're going to hop over to our periodic table. Here is aluminum, folks. It's actually in group 13, so it has 3 valence electrons, and as you recall, aluminum would be 3 positive. Bromine is over here. It's in group 17. It's a nonmetal. It has 7 valence electrons, so it's 1 negative. So the formula for aluminum bromide is AlBr3, and that's a solid. Now, this equation is not balanced yet. We're going to learn how to do that shortly. We're just learning how to write the reactants and the products of an equation right now. Let's try this one. Solid carbon reacts with sulfur to produce liquid carbon disulfide. Why don't you take a minute and try to write that reaction? Then come back to the video and see how you did. Okay, welcome back. Solid carbon. So carbon elementally is C, and it's a solid, so I'm going to put an S after it in parentheses, with solid sulfur. Sulfur is S, and in parentheses we're going to put an S because that's also a solid, to produce liquid carbon disulfide. So carbon disulfide, that's a nonmetal to a nonmetal, we use prefixes to tell us how many of each atom is present in the compound. So carbon disulfide means CS2. Now that is a liquid. Now, did you have something like that? Great. So once again, the things on the left of the arrow are called reactants. And the things to the right of the arrow are the things that we form, and we call those the products. All right, as I mentioned a moment ago, there are 7 elements that cannot exist by themselves, even when they're isolated from any other type of atoms. Elements of this nature will combine with atoms of the same element in order to be stable. They are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Now, if we use the symbols of each element, you end up with the following, right there. Now, my high school teacher called these the Brinkelhoff elements, because they spell out, if you use the symbols, Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. And they are all diatomic, so they would be in their elemental state Br2, I2, N2, Cl2, H2, O2, and F2. You should memorize these. Once again, an easy way to remember them is by using the acronym Brinkelhoff. Now, you may notice that the equations above were not balanced. This means that there are not the same number and type of atoms on both sides of the equation. Now, the law of conservation of mass requires that there are the same number and the same type of atoms on both sides. Now, we won't worry about balancing the S, the L's, the G's, or AQ's in the balance, in the equation. Once again, those are just state symbols telling us what phase they're in at that particular temperature. So you can see in this equation that we did at the end, the carbons did not balance. There's one carbon atom here and one there. Sorry, the carbons do balance, but the sulfur, there's one over here and 2 over here. So according to the law of conservation of mass, that can't happen. We have to have the same number and type of each atom on both sides of the equation. The equation up above, 1 aluminum and 1 aluminum, they're okay, but there are 2 bromines on the reactant side and 3 on the product. So how do we fix that? How do we account for those? Well, that's where we're at next. Balancing chemical equations. To balance an equation, we must first find the correct coefficients for the chemical formulas in the skeleton equation. A coefficient in a chemical equation is the number written in front of the reactant or product. Coefficients are usually whole numbers and are not usually written if the value is 1. So we leave them off if the coefficient is 1. The coefficients in a balanced equation describe the lowest whole number ratio of the amounts of all the reactants and products. Please remember, never change the subscript. So there are subscripts in the formulas of a compound, and those are never ever changed to balance the equation. Now, the best way to learn how to balance equations is to simply practice. So we have a bunch of examples here. Hopefully, by the end of this video, you'll sort of get the feel for this and feel fairly comfortable with balancing equations. So let's take a look at the first one. We have solid copper reacting with gaseous oxygen. Notice it's O2, one of my diatomic Brinkelhoff elements, to form copper 2 oxide. Now, there's 1 copper on this side and 1 copper on the other, but there's 2 oxygens on this side and only 1 over here. So, how do we balance those? Well, let's take a look. If I were to put the coefficient 2 in front of CuO, wouldn't that now give me 2 oxygens on the product side? That would mean I have 2 copper 2 oxide units formed. That gives me 2 oxygens. But of course it also gives me 2 coppers. So I need to balance the copper on the other side because I've only got 1 of those. So can I add a subscript 2 here? No, if you were listening, we can never ever add and we can never change subscripts. We can only mess with the coefficients. So I can put the coefficient 2 in front of the copper atom. Now I have 2 copper atoms on both sides and 2 oxygen atoms, and this equation is now balanced. Let me do another one for you. Potassium and liquid water react to form potassium hydroxide dissolved in water and hydrogen gas. So I have 1 potassium on both sides. I have 2 hydrogens here. I have 2 over here, but 1 more for a total of 3. Those do not balance. I have 1 oxygen and 1 oxygen. So let's go ahead and try to balance the hydrogens. So how are we going to do that? Well, let's see. What if I put a 2 in front of KOH? See what that does for me. It gives me 2 hydrogens plus 2 more is 4. If I put a 2 in front of water, won't that also give me a total of 4 hydrogens? But on the reactant side, I have 2 oxygens on the reactant side and 2 oxygens on the product side. I have 2 potassiums on the product side, so if I put a 2 in front of the potassium here, I now have 2 potassiums on the reactant side. Now I believe this reaction is balanced. Let's check. Potassiums, there are 2. Hydrogens, there are a total of 4, because I have 2 H2O molecules. And oxygens, there are 2. On the product side, I have potassiums, which there are 2. I have oxygens, which there are 2. And I have a total of, let's see, 2 hydrogens here plus 2 more, which is 4. And if you look, the number and type of atom on both sides of the equation is balanced. All right, let me do another one for you before I have you try one on your own. The next one, calcium chloride dissolved in water reacts with sodium sulfate dissolved in water to form calcium sulfate, solid, and sodium chloride dissolved in water. Well, let's take a look here. It's been my experience that if we see oxygen, sometimes it's nice to balance that last. So actually the oxygens look like they're in pretty good shape. So let's take a look. There's 1 calcium here and 1 over here. There are 2 chlorines here and only 1 on this side. So let's put a 2 in front of NaCl. Won't that now give me 2 chlorines? Of course, it also gives me 2 sodiums, which is nice because I need that. And then do you notice that the sulfate, this polyatomic, travels as a group? If you see the polyatomic traveling as a group, you can balance it as a group. So if there's 1 sulfate on this side and 1 sulfate on this side, they balance. So let's erase these arrows and other things I've drawn in there might confuse us a little bit. And let's see if this equation now balances by me simply putting this 2 in front of NaCl. 1 calcium, 1 calcium. 2 chlorines, 2 chlorines. 2 sodiums, 2 sodiums. And a sulfate on both sides. Yeah, so that equation balances by simply putting this 2 in front of NaCl. Why don't you try the next one on your own? So pause the video, take a minute, and give it a try. All right, did you have fun with that one? Yeah, that was a little bit different than some of the other ones we did. Let's see how you did. Let's see, we have this ammonium ion right here, but it doesn't travel as a group, so we can't balance it as a group. So let's take a look at the atoms that make it up. I have 2 nitrogens. Remember, a 2 on the outside of the parentheses mean I double whatever's inside. And on the other side I have 2 nitrogens, so I feel good about that. I have, let's see, NH4, and there's 2 of them, 8 hydrogens. On this side I've only got 2 hydrogens. Let's balance the hydrogens at the end when I balance, and I'll use water to balance it. So let's hold off on my hydrogens. Let's check everything else first. Chromium, there are 2, and there are 2 here. 7 oxygens, and only 3 over here. All right, let's see. Well, let's erase a few of these stray marks here to clear it up a little bit. See how we do. I needed to get 8 hydrogens, remember? So I'm going to put a 4 in front of water right there, and that gives me 8 hydrogens. Now my nitrogens we know were already taken care of. My chromiums were already taken care of. I have 7 oxygens here. Don't I have 3 on the product side here, plus 4 more over there, which equals 7. Yeah, so that equation is balanced simply by putting that 4 in front of water. Now, did you make it that simple? Probably not. And you're going to find that it's probably easier for you to use a pencil to balance these equations than a pen. So you can fix your mistakes. Sometimes it's just nice after you try after a while and just erase everything and start again. All right, let's do one more in this video, and then we'll save the others for another, okay? All right, carbon dioxide gas reacts with liquid water to produce C6H12O6 solid. That's glucose, by the way, and oxygen gas. All righty, we've got 1 carbon here and 6 there. Let's put a 6 in front of CO2. That gives me 6 carbons on both sides. Now, let's take a look at my oxygens here. I have 6 times 2 is 12, plus that one over there. Let's hold off on those for a minute. I think I can fix my hydrogens right now. There are 12 on the right side. If I put a 6 in front of H2O, doesn't that give me 12 hydrogens on the left side? So they balance? Now we're going to have to fix my oxygens. We don't have any other choice. So we have 6 times 2, 12 oxygens there, and we have 6 more for a total of 18 O's. I have 6 oxygens there, and so I need to get 12 more. What if I put a 6 in front of O2 here? Won't that give me 12 more oxygens on that side? Yeah. So I have 6 plus 12 oxygens, 18. I have 12 plus 6 oxygens on this side, and that's 18. So let's clear this up a little bit. So it looks like there's a 6 in front of O2 on the right-hand side, a 6 in front of water on the left-hand side, and a 6 in front of CO2. If you take a look, that equation now balances for us. All right, that's good enough for now. We're going to come back on the next video, and we're going to practice some more of these. See you soon. Bye-bye.